Hello folks, welcome to the second video in my series of how to implement Tetris in Erlang. If you saw the first video, in that video what we did was we started with a blank template project that was templated by ZX. Then we added some data models to it to try to represent the playing board that's called a well in Tetris. Then we made a data model for the piece. When I say data model, I made an abstract data type represented by modules. So there's an ET piece. Like we can just look at, well, yeah, we can look at it here. This module represents pieces. This module represents the playing field. And then as the final step, we set it so that when we run the program, a random piece is generated at startup time, and it's shown displayed into the well. So we verified that our data model is not too crazy, that our functions that we've written interpret that data model correctly, and that the sprites that we want to put on the screen don't look completely ridiculous. So this is the Erlang repository. We've got a commit history. So there's the first one, second. This is where we got to in the last video, was draw the board with a random piece on it. Let's run this and take a look at how it is. Okay, so we've got a line that was randomly generated, and we'll get something else. So each time we run this, we should get, just a random piece will be drawn on the board in this area. And that's it. And the board looks like a Tetris board, so I'm happy. One thing that you'll notice is that when I run this, a bunch of junk behind us like pops up on the screen. If I press a key, more random stuff pops up on the screen. It's not actually random. This is the program state. So the GUI is showing us that unexpected event, a WX event of an unexpected type is showing up here. The event itself is a WX key event of char hook. What a char hook is any character that you press on the keyboard that the window manager sends to your program. So this is a little bit different from key down, key up. If you're seeing if a user has held a key for a long time, you get a key press down event and you get a key press up event. Same thing with mouse buttons. You get mouse down, mouse up, and that's how you implement like drag and drop and stuff like that. Or if you have a 3D world and you have a coordinate, a mouse down event here, you want to rotate something. Like in a game, you're building your character and you can rotate them around in 3D. You get a mouse down event and you note where the mouse coordinate was. Then every mouse motion event, while the key is held down, you rotate a little bit until the mouse up event happens, and then you come out of the rotating mode. You can do the same thing with keyboard stuff. Hold down Alt while you do something. You check if Alt is being held down. You've got the key down, key up event, and whatever. Char hook is not that. What char hook is every time the GUI says there should be a key input event for like whatever character or whatever key code value should be going to the whatever window is in focus. That is char hook. So if somebody holds down, if you open a text editor and you hold down the letter A, after like a second or so, most GUIs will start drawing A really quickly on the screen, right? Each one of those, there's no unique key press down, key press up event, right? You're just holding it down and you're getting more A's. Those are char hooks. And that's what we're checking for here. The reason that we want that in particular in this game is that when a player holds down right or left or down motion, after a second, that piece should kind of zip off to the right or left or down. That's an important feature of the game. So char hook, I'm catching char hook, and the reason I'm drawing all this on the screen is one, you'll notice that you see the little S piece here is this S, the S's here are being drawn there. So I can compare that visually and see that it's correct. And I can see what the key value of any key that I push is. So if I don't know the key value for left. Let's check. Okay, so 314. That's the key value for left. So I can start discovering these key values so I can write event handlers that match on those values as the next step. And that's pretty much what I did. So what we're going to talk about today, starting from this point that we left off at in the previous video, we're going to continue on with implementing unsafe movement, which is this commit. And then we're going to culminate with movement, proper, like safe movement, can't go out of bounds type safety, line completion, and board clearing. So we're going to jump up to this commit and see how things work. Run this and see what happens. So if I press space, I get a random piece. Instead of starting off with a random piece, I get a random piece by pressing spacebar. So if I move down here, I can go left and right because we haven't locked into the board yet, right? You have to press down to lock into the board. Down motion is required for board locking. Now let's check boundaries. Does this work? Yep. I can't go too far that way, and I can't go too far that way. And every time I hit the bottom, the piece is locked into the board. Now, if I hit another piece, I should also lock into the board, which I do. Okay. Now, let's check this real quick. I should not be able to rotate left or rotate right. Neither one of those work if I'm too close. And the same thing should be true if I'm down. Might be able to rotate. Okay, I can rotate one direction here, but I get stuck, right? So that is correct behavior. Now, line clearing. Let's see if I can clear a line. You notice that every time a piece locks into the board, we get a terminal message here that says complete none. What that's telling us is that, like, what lines were completed. If I do this now, okay. Complete 18. Row 18 was complete. Now the coordinate system here starts from 1 at the top and goes to the bottom. So the first row at the very top is row 1. The bottom row, this is an 18 block height Tetris well. So the bottommost line is line number 18. So let's do a multiple clear and see what happens. Okay, so I hit Control or Alt or something, and the key code was shown on the screen. Okay, let's clear 2 lines. We should see lines 17 and 18 are cleared. Okay, and they are. And the well was collapsed correctly. That's important. So on that note, let's actually leave a mess right here. Are we going to clear this line correctly and leave all the correct artifacts in place? Yes, it works like it's supposed to. Yay. So how did that work? Why does it do that? And how did I make it do that? We'll check real quickly. So the interesting stuff here is going to mostly be in the control module. There are a couple of changes to the data. Let's check the data real quick, just to kind of knock it out. I think that piece has a new... Right, so originally we had random, new, flip. We had points 1 to get the offsets. We had type. Okay, and sides, that's new also. So points 2 and sides are new functions. Now the reason that there are points 2 is that previously, in previous code, the controller had been calculating the offsets necessary to place the occupied points by a piece into the board and then updating a fresh well and sending that off to the GUI to redraw the entire well every time. That is, you know, not necessarily a good way to do, you know, we don't want to redraw the entire screen every time. You could start getting flicker, or, you know, there could be weird things. So anyway, the reason that this function actually moved into piece, because the offsets had been previously arbitrarily calculated inside of a lambda or a closure to show it, like just to put stuff into the board. Now the board is one thing and the piece is a separate thing, because the piece cannot be part of the board until it's locked. Until it locks into the board, the piece is one thing and the board has to be a separate idea. Otherwise, we can't detect collisions and stuff. So points 2 is this. So if you remember, points takes an orientation and a type, and it returns us what the offsets are. What points 2 does is it takes a current piece and a location, and it updates, it translates this function here that's being defined. We have to close over these two values. So the offset points are going to be the input values to this function, and it's going to add the offset by the location. And that's going to translate the offsets to an actual location and then give us the points back. And this is going to be an important function, both for the GUI, has to be able to call that, so it knows where to draw a piece, if we're only going to draw a piece, or, you know, some list of points. And the controller has to be able to call this function also, so that it can calculate collisions and rotations and stuff like that. So this is necessary for both of them, especially if a piece locks into the board too. You have to know where it's locking in so it can update the well. So that's changed here. Sides has come in because we need to know the maximum extent of a piece now, because we are checking boundaries left and right. So there's two types of collision checks. One check is, are we going out of bounds? If we're going out of bounds, then, you know, we have to disregard the movement. And the way that we know we're out of bounds or not is we don't necessarily want to go through every single possible point. We would rather know how wide is a piece and how deep is a piece, so that we can, like, real quickly just know, are we going off the side or not? So this function for sides works very similarly to the offsets function, in that it takes as its input a piece type and an orientation, and it returns how far off to the left is it offset, how far off to the right is it offset, or are the sides, how wide is it left and right, and how deep is it, how far below the current point does it go down. And that's what all these are. These are just boundaries, like how big is the activity box for this thing, and that's it. So if we go look at the well has changed a little bit too, because remember, we have to know if the well is complete or not. So originally we had the dimensions functions, we had a height. Actually, height and width are new. Breaking those out as their own functions is a new thing. And we'll see, there's a couple useful cases for that in the code later. Fetch and store were originally there as well in the first version. Complete and collapse, those are new. So complete, we get a well, and we want to check if any of the lines are complete. So the way we do that is we check, we get the dimensions of the well, how wide is it, how high is it. Then we make a function here, case complete of nothing's complete, we return none. If we get a list, we're going to return the list. And then remember, in the terminal just now, whenever I would lock a piece on the board, we would get this message, complete. So this little debug message is here. tell is a ZX thing that prints the message both to the log file and to standard out, so we can actually see it as we play. And then return complete. So complete is going to loop over, starting at 1. It's going to start with the first row. It's going to remember the maximum extent of the thing, so that this is why, so that we can, if the current coordinate is less than or equal to the total height, then, you know, run this. If not, and we have oh, that's interesting. So I've got like case complete here, and then actually I'm returning none from inside of this. So that's silly. Whatever. So this will never match probably anything. And like, who cares? I probably fixed that later. If not, I'll go back and fix it. It's not a big deal. Anyway, case line complete. So we're going to pull one line out of the well, and we're going to check it from 1 to the maximum extent, however wide it is. So is this line complete? If the element at the current coordinate is x, then no, that line's not complete. If the element is anything other than x, at least when we start out, then we want to keep looping. We're going to keep iterating over this until we're completely out of these. So if we go through every single element, every element in that row, and all of them are not an x, then we return true. If any of them are x, we shortcut. We don't have to check anymore. We know there's a gap, so we just return false. So if line complete is true, then we're going to add that index, the number of the row that we just checked, to the complete lines count. If it's false, we're not going to add it. We're just going to iterate and keep going. Once we've gone through every single row, we're going to return one of these two cases, which, again, this is silly. Like, I really should just return lines, because up here we're matching on the empty case anyway. So whatever, it's not a big deal. But that's how complete works. We're just checking that everything in each row, we're just looking for rows that have any x's in them to mark them false. And if anything other than x is the value at a given spot, then, or, you know, across the entire row, then return true, which will ultimately give us a list of the completed lines, or the atom none. And that's it. Collapse. So how do we collapse a well? We've got a well. We have some lines that might be cleared, and we want to loop over some function that's going to give us a way of removing a line that's complete, remove that from the tuple, and we need to add a blank line to the top. So what collapse does is we create a row, a blank row. This returns us a blank row that's the same width as the well. So width well row, get a blank line. Then crunch is a function that we're going to use to fold over the well itself. And what that does is we get the line. Well, actually, we get the line number, and we have the well, and we have an offset. And the reason the offset is important is that, remember, we have line numbers that have been completed already. So let's say we've completed line 18 and line 16. Now, if I start off removing either one of those, and I move the field jumps down, like if I'm trying to remove from the bottom and going up or something, the coordinate for the place I'm looking to delete just changed. So if I'm going from the top to the bottom, and I remove stuff, everything's moving, so the lines I'm trying to remove become moving targets, which is, that can make it hard to figure out. So we start with, we got our biggest lines first, right? That was the order of the list. And due to that, we're going from the bottom to the top. So we have to offset as we go. That's what this is about. So we're going to remove an element on top. Then we're going to insert that new blank line. We're going to insert that at the very top. And then we're going to return the crunched, and this becomes our accumulator value. And we're going to start with the well and with 0. And that's it. We're going to loop over that and then return element 1 of the return. Remember, this is getting returned back. This function here, this function call over fold, is going to return this updated accumulator, and we only want the well. We don't need this offset number. We only need the well. So we're going to return element 1 of this fold. That's why this is wrapped in element 1. So what we see here is how we check completed lines, that we return a list of the completed lines that we found. And we can take the well and we can collapse it. If there's any lines that are complete, we can collapse those down and update the well to crunch stuff down. So that's how that works. Now, the guiding logic behind all that is over here in the controller. If we look at, we remember rotate, right? Like rotate and move, it's simple how those work. When you don't have anything around and we don't care about borders, you don't care about collisions or anything. So now that we do care about collisions, everything changes. So do rotate is going to match on the case that we don't have a piece, because we're no longer starting up the game and then just like getting a random piece up. There are cases where we're not going to have an active piece, so we have to accept a do rotate input without crashing. So if there's no piece, just return the state. When we rotate and we do have a piece, we need to assign the piece, get the current location, the current well, because we need to evaluate all these, and the direction, because direction is going to tell us if we're rotating right or left. We need to determine if it's legal to rotate right or left. Are we trying to put one block out of bounds or something? Or are we going to rotate through an existing piece that's in the board? So do rotate, the first thing it does is it evaluates the rotation. If the rotation's okay, it will return back a list of the vacated blocks, the places that, like if a line moves, right? One of those blocks in the line is still there, but 3 of them have been removed, right? So we need that list of those 3 so we can overdraw those with the little X, the black square. We need another occupied one so that we can draw the correct type for that piece type in the new location. And we need the new piece so that the state record can remember it. Update the state record so that it knows what the orientation of the piece was. So eval rotation can return OK and the data relevant to displaying that the rotation occurred, or it can return stuck. And if it's stuck, meaning the piece is hitting something or it's out of bounds, it's just going to return the state. So let's take a look at how we eval the rotation. We need to know the direction, the piece, the location, and the well. So we're going to flip the piece and get a new version of the piece that represents it having been flipped. We're going to get the points. Remember points 2 from the piece module. The new orientation of the piece combined with its location should give us the new points it will occupy. So we get the points list. Then the dimensions of the well, the width and the height. That's important because remember we're checking if we're flying outside of the well. And we check like this. So we have open, which is this is a Boolean a Boolean function that's going to accept an XY coordinate, and it's going to check, is it in bounds? Is X trying to go, is X 1 or greater, or is it the maximum width or less? So is it in that range, in the legal range there? And then also, is Y not poking out of the top and not trying to poke through the bottom? If both of those are true, if X is in bounds and Y is in bounds, then we return true, and we're going to check. Note, there's a comparison here. We're going to do one more comparison, which is we're going to fetch the element from the well at that spot. And if that element is X, then it's blank, and it's true. It's true that that spot is open. If, however, any of this is false, we don't have to check the well. We know it's false, just period. Then we're going to check all of the points that are the new location points. We're going to check all of them with open. Now note that the open function here, this lambda, is closing over the well, so it can check the condition every time. So that's why this is not, that's why open is not a named function. It's an anonymous function because we needed to make a closure to close over the well without, being too noisy. So lists all open points are all the points that we're trying to check open. If they are open, then the rotation is okay. And we need to get the point difference between the old piece and location, the old aspect of the piece, and the new points that it's occupying. And we'll get the vacated points, and we'll have the occupied points, are the currently generated points. And we'll return OK, vacated, occupied, and the new piece. Then it will carry on, get the piece type, and it'll call GUI show, which has changed. GUI show now does not accept the whole well. The show function can now show just a certain type of data. So we can show a list. We're going to overwrite the vacated blocks. We're going to write the newly occupied blocks with that type. And that will make it look, that'll affect the animation that we want. If we return stuck, if any of the points are not open, then it's false and we return stuck. And then we just don't do anything. We just ignore that someone tried to move. And that's it. That's rotation. Pretty simple. Do move is a little bit more complicated. And I broke do move up a little bit differently. I think I actually wrote motion first, and then I wrote the rotation second. And the way that this check happens, we've got a boundary check and a location check at the same time. And I didn't, that's the second time I thought about the problem was when I was doing rotation. I did motion a little bit different, and we'll see. There's neither one's right or wrong really, but we'll see. In the motion one, what I do is I do a boundary check first to see if it's blocked, if we can't do the motion. And then collision check is different. Collision checks to see if we actually hit a block that's somewhere in there, which I kind of like the rotation way more. But anyway, we'll see how this one is. So if we don't have a piece, we're going to ignore it. Okay, and then I've got a commented out thing here. If the motion is bottom, which we have not implemented yet, and that's why this is commented out. It's to remind me to implement this. Bottom, we have motion left, motion right, motion down, right? We also have motion bottom, meaning that it's a hard drop. If the user hits spacebar, the piece should immediately go to the bottom, right? That move is not implemented yet, so this is just commented out for now. So if the direction is left, right, or down, we're going to get, again, the relevant stuff, the piece, the old location, and the well. And then we're going to project. If we did move, would that motion location be legal or not? So we're going to check if it's blocked. And the way blocked works, well, okay, before I get ahead of myself. Up here in rotation, we did evaluate the rotation, and the results could be okay or stuck. in this one, in doMove, we have a new thing. Check if the motion's blocked, if it's like inbounds. It could be okay, it could be stuck, or it could be locked, because we're moving, not rotating, right? Motion down, and you hit anything, you hit the floor or you hit another piece, locks the thing. So you're not just stuck. You can be locked, and locked requires a different set of actions. So if we check whether we're blocked and we're okay, we move on to the next doMove function. There's two doMoves. We proceed on to the next step of doing a motion, which this is the same name as this function, but the arity is different. So sometimes I do that. It's not a big deal. Sometimes I do doMove 2. If it gets complicated, I always like start numbering the steps. But in this case, I just use the arity to differentiate between the second step of move. So doMove, we're going to get the new location. It's not blocked, so it's inbounds. It's an inbounds move. We're going to get the occupied points of the new location. Then we're going to check those points against a potential collision. Did we actually hit anything or not? And if we don't have a collision, then we're good to go. If we do have a collision, then we're stuck or we're locked. So same thing. It's okay. We're stuck or we're locked. It's okay. We're stuck or we're locked. So blocked is just a boundary check, I believe. So blocked in the direction, in whatever direction. Here's the well at these coordinates, and then the piece. So we need to get the dimensions. We need to get the sides. Remember, we're not getting the points. We're getting the sides of the piece. The left extent, right extent, and the bottom. We're getting the maximum extent, which is width minus right. We're getting the maximum left bound, which is 1 minus the left bound. And we're getting the maximum bottom, which is the height minus the bottom extent. Then direction. If we're moving right and x is less than maximum right, then it's okay and we can update the coordinate. If we're going left and x is greater than max left, then it's okay. If we're going down and y is less than maximum bottom, then it's okay, we can go down. But if we're going right and x is bigger or equal to that, we're stuck. If we're going left and x is less than or equal to max left, we're stuck. And a special case, if y is greater than or equal to the maximum bottom, then we're locked. We've hit the very bottom of it. So we'll look at what lock does in a second, because it's called in both these cases. So doMove. Direction, new lock, state. So we've got the new location generated here already. The occupied points have to be known. We're going to check if there's a collision with anything in the well now. So how do we check collision? Collision's pretty easy. We're just going to loop over the occupied points, and we're going to fetch the thing. So we've just got a simple case here. We're going to fetch whatever is at that location in the well, and if it's x, if it's empty, if it's not, there's nothing there, then we're going to call collision on the next point, and we're going to loop all the points. And if all the points are x, if they're all x's, then we're going to wind up down here with an empty list, and we can return none. There were no collisions. If, however, we fetch the thing at x and it's anything other than x, fetch the point xy in the well, and if it's anything other than x, but we're going down, then we are locked. That means we hit something, we hit a thing. If, however, we got something other than x, but we're not going down, meaning we're going left or right, then we are stuck. So that's how this collision check works. And I wrote it broken up like that as opposed to the rotation one, because I wrote this first and I was just thinking through, well, I have to do a boundary check. Okay, so if I have the sides, then I know that that's true or not. And that would be, so I can do that. So I wrote the sides function, and I figured out how to check these in a way where we capture every possible case. Then I was like, okay, we got to do collisions. Collisions with other pieces to determine if we're locked or if we're blocked, or if we're locked or if we're stuck somewhere. And so I wrote that separately. Later, I already had that in my mind, and I wrote the rotation stuff. And the rotation stuff, this actually does the job of blocks, of the blocked function. And this inner check does also the job of the collision function. So we could actually we could get rid of blocked and collision. I could write an eval move function that combines these, and then I wouldn't have a two-step move. I'm still going to have to check for stuck or locked condition, but that could be worked into it. It's just, I did it a different way. It's not like a big deal. It's kind of nice to be able to see two different implementations of actually kind of the same thing, one that combines it together. And some people would argue that this is bad because I've combined two checks into one thing. They're not independent checks. It's a single check of all cases at once for rotation. And, people may say that's dangerous. I don't feel that it is, but some people would say that combining them like this is not good. So anyway, the way this worked out is that do move checks if it's blocked, meaning if it's in bounds, and the next do move step checks if it's a collision or if it's in bounds. Either one of them can decide that it's stuck or that it's locked. So locked, we're going to look at locked now. What locked does is it knows the occupied spot that you're going, and it knows the state, and then you see all the stuff getting pulled out here, what the score is, what the lines are, what the count is, what's the delay, what's the piece, and all that. So we've got some new stuff happening here. The reason all this stuff has to get pulled out is in the event that we check the complete lines, and none of them are complete, we just return the lock score lines, whatever, and move on. If we do have completed lines, though, we have to clear them, calculate a new score, update. We have to update the GUI with all this new information. So we're pulling out quite a bit from the state at the head of this function. And I think this function is probably the most, maybe one of the most complex in the whole game. So anyway, we get the type of the piece out. We're going to, remember, this piece is becoming a part of the well now. So remember previously in old versions, we had the place function, which like folded over the well with the type and stored everything in there. Now we have a place lambda that does the same thing. And we're going to fold over the well and return the new well is called locked, the locked version of the well. This has been updated now. But this isn't the final well yet. We're still going to check whether or not lines are complete. So there's two parts of updating the well here. We're going to lock the piece in place in the well. So that's the locked well. The piece itself is gone. We're going to need a new one. Then we're going to check the locked well for completed lines. If there's completed lines, we need to collapse the well down. That'll be the final well. That'll be the new one. But we don't know if we need to do that step or not yet. So we lock the piece into the well. Then we call complete over the locked well. If no lines are complete, then the locked well becomes the final well. The existing score is the new score. The existing line count is the complete line count. If, however, we have a list of completed lines, we're going to call that etWellCollapsed function over the locked well, telling the well which ones are complete so that it can collapse them. And we get the collapsed well back. Then we need to get the line count. How many completed lines were there? We want the line count. Then the next lines, next lines meaning the next number that we're going to tell the GUI to show, is the line count, the current line count plus the lines is next lines. The current score plus this calculation for developing the score. So this is the increment, how much we're going to increment the score by, adding that to the score is the next score, and then updated. Now I'm just breaking this out as a labeled variable. We want the GUI to show the updated elements. Well, the updated elements are the collapsed well is the new well, the next score is the new score, the next lines are the lines, and we need to remember this stuff in state. So we're going to, breaking out of this case, we're going to assign that the new well is the collapsed well, that the next score is the new score, and the next lines are the new lines. Then we're going to get a new piece. We're going to put it at, again, these are magic numbers, arbitrary location. We're not like deriving a location, based on the size of the well, which we really should do later, which we do later, but in this version, I don't care yet because this is not the problem I'm trying to solve yet. We get the new points of the piece. So we got the new piece in the new location. And now remember, this is always true. It doesn't matter if we've completed lines or not. We have to get a new piece regardless because we just locked the old one. It's gone. We've got a new type. And we have a new count of how many pieces have been used in the game so far. Now we're going to call etGUI show again. Show the occupied type at these new points and show the new count. So the GUI is going to update this. So it's actually going to get two messages from us if there's completed lines. It's going to get the show updated stuff and then show the new piece and new piece count stuff. Then we're going to return the state updated with the new well, the new piece, the new location, new score, new lines, and new count. So this is, probably the most complex function, or at least it's the most to read through in the game. And it's not, when you break it down, it's not that hard to understand, but there is a lot happening in here. And the semantics of store this in the well and collapse the well, collapse the locked well down, I think those are fairly easy to understand. But, so you wouldn't have to know how those are implemented to use, to read this function or to edit this function. Note, some things could be, handled a different way here. We could do well complete with locked and return, this returns none. We could do check complete and return an already collapsed well with a line count. We could certainly do that. I just didn't here. I broke out the completed, check if there's completed lines as one function, collapse well back down as a separate function. They didn't have to be. I could just do collapse, and collapse could return that nothing changed or that there were completed lines of this number and whatever. I could have done it either way. It doesn't really matter. What matters to us most of all is that we actually have that, that version of the code that actually does something. So finally we can actually, move this around, and we can do completed lines and stuff. Now notice what's happening here. We haven't fully implemented clearing things or clearing the board, because we can still do random pieces right on top of each other. So none of that's done yet. But basic motion, the basic motion rules, and the basic line clearing rule, and the way to collapse the board down and draw stuff correctly, that all works by the time of this commit. So let's see if we could... We're running a little bit long on time, so we'll look at this one commit. Let me check in here and see if this is long, then I'm going to do it elsewhere. Oh, yeah, that's delay and scoring. So, okay, I'm going to go over, because that's like real gameplay stuff. We've got motion, basic display, basic mechanics are done up to this point. So this is what? Commit 1, 2, 3, 4, 5, 6, 7. So the 7th commit is how far we've gotten here. And up to this point, we've implemented display. We've implemented basic gameplay mechanics. And the thing works basically safely. And we know we're on track to build a game that works the way that Tetris is supposed to work. But we don't have the timing yet. We don't have really proper scoring done yet. We haven't implemented levels because we don't have a tick. There's no game tick. With no game tick, you can't have Tetris, because Tetris, the whole reason Tetris gets hard is that tick gets faster and faster as you increase levels. So none of that exists yet, but the basic mechanics are in place. And I think if you've done any Erlang in the past, or even if you haven't done any Erlang in the past, you could probably... Even an inexperienced coder could look at this code and think about it carefully and probably come up with a way. If they looked up the documentation for Erlang and looked at like how to send a message after a delay, you could probably figure out pretty quickly how to finish the game from this point. You wouldn't have to be, you wouldn't really have to be too familiar with Tetris even to complete it from this point. So I'm going to stop this one here, and I'll make another one, another video that goes on, and we do the timer, set, final gameplay features, and implement hard drop and game over conditions and things like that. And I'll, right now, like even the finished version 1 of the game, actually doesn't save scores or anything. So I might add that as a feature. And we can look at actually how you would remember stuff like that and pull it back up to show people things, and kind of make it more polished. I may do that. And that would be maybe a 4th video. I don't know, but we'll see. Next video is going to be on, final gameplay rules. We got mechanics done. We don't have rules yet. So we're going to go ahead and do rules and also implement the tick, and that'll be the next one. So thanks for watching up to this point, sticking with me this far. I hope my explanations are clear enough that you can go through the repository yourself and kind of look at things and figure out how they work based on, my explanation and reading the code. And if they're not, sorry, I hope I'm clarifying more than I am confusing. So have a good time out there writing code, and have a good rest of 2020, which is all kicked all of us in the balls. So bye now.